All right, today we are going to tackle one of the most powerful and honestly one of the most dangerous numbers in all of science, the p-value. It's a number that literally shapes thousands and thousands of studies, but it's so often misunderstood. So let's demystify it once and for all. So here's the crazy thing. The p-value is the cornerstone of how we test things in science, right? It's used in countless papers every single day. And yet, it is so widely misused that it has sparked what many are calling a replication crisis in science. How can one single number be so important and at the same time so incredibly confusing? Well, we're going to find out.
To get a grip on the p-value, we first have to understand what it's arguing against. And that starts with a little something called the null hypothesis, or H0.
Okay, just think of the null hypothesis as the default, kind of boring state of the world. It's the ultimate skeptic. It's the assumption that, there's no effect, there's no difference, nothing to see here. Our new drug doesn't work. The two groups we're comparing, they're the same. This is the baseline, the thing our experiment is trying to prove wrong. Okay, so with that nothing is happening idea in our heads, let's bring in the star of our show. I think the best way to think about the p-value, at least to start, is as a surprise meter. Now, here comes the official definition. And I really want you to listen to the very last part of this sentence. The p-value is the probability of seeing your data, or something even more extreme, if that null hypothesis of nothing interesting is happening were actually true. That last part, assuming the null hypothesis is true, that is the key to everything.
So if our surprise meter gives us a really small number, like a tiny p-value, it's basically screaming at us that our results would be incredibly unlikely if the null hypothesis were true. And that rarity, that surprise, it makes us suspicious. It makes us doubt that whole nothing is happening scenario and start to think, maybe, just maybe, something is going on here. Historically, people haven't even agreed on how to use p-values. It's kind of funny. On one side, you have this guy, Fisher, who saw it as a spectrum of evidence. The smaller the p-value, the more you should doubt the null. But on the other side, you had Nyman and Pearson, who saw it as a simple yes or no decision tool. You pick a line in the sand, like 0.05, and if your p-value is below it, you reject the null. End of story. This tension between these two views is actually where a lot of the confusion comes from today.
And oh boy, has that confusion led to some big-time misinterpretations. Now that we have a feel for what a p-value is, it's even more critical to talk about all the things it is not. This is probably the biggest mistake out there. Someone sees that p-value is less than 0.05, they get all excited and they shout, "My effect is real, my theory is true." But that is just not what the p-value is telling you. Nope, absolutely false. Remember, the p-value is calculated assuming the null is true to begin with. So it can't possibly tell you the probability of the null being true. All it tells you is how well your data gets along with that null idea. A small p-value just means your data and the null hypothesis are not good friends. Okay, now for the other side of that same coin. A researcher gets a result with a p-value higher than 0.05, and they conclude, well, my study proved there's no effect. Wrong again. A high p-value doesn't prove the nothing is happening scenario is true. It just means your experiment didn't kick up enough fuss. It didn't provide strong enough evidence to make you doubt it. It could be there is a real effect, but maybe your study was just too small to find it. You got to remember this phrase: absence of evidence is not evidence of absence. Now this one feels right, doesn't it? A super duper small p-value, like 0.001. That must mean we found something massive, a huge discovery. And you guessed it, also false. This is so important. The p-value tells you nothing, zero, zilch, about how big or how practically important an effect is. You can get a microscopically small p-value for an effect that is completely trivial and meaningless in the real world, especially if you have a giant sample size. Statistically significant does not mean scientifically important. So whenever we use a p-value to make a hard yes or no call, we have to live with the fact that we might be making a mistake. We could have a false positive, that's a type 1 error, basically crying wolf when there's no wolf. Or we could have a false negative, that's a type 2 error, where we miss a real effect that was right there. A p-value is really just designed to help us control that first kind of error, the false positives. So if the p-value is so tricky and so limited, what's the answer? The answer is to never, ever, ever rely on the p-value by itself. You need to look at the whole story. A much better analysis always looks at three things working together. First, yeah, the p-value. It's our is it surprising meter. But then you absolutely need the effect size to tell you, okay, but how big is the effect? Does it matter? And finally, you need the confidence interval, which you can think of as a range of believability. It tells you how precise your measurement is. Let's see how these three musketeers work together.
Let's make this real. Imagine there's a biomarker test where the average score is known to be 50. We test a new group of 25 people and their average is 53.2. So the question is this difference real or is it just random noise?
First, we run the numbers and get the p-value. It comes out to about 0.122. Now, since that's bigger than our usual cutoff of 0.05, a lazy analysis would stop right here and say, "Welp, not significant, nothing to see here, folks, move along." But that's not the whole story at all. Because now we move to step 2. We calculate the effect size, in this case something called Cohen's d, and we get 0.32. Now, that number might not mean much to you, but by convention, that's considered a small to medium-sized effect. So, hold on a second. The p-value said nothing to see here, but the effect size is whispering, hey, there might be something kind of meaningful here.
And now, we bring in the third piece, and we get the complete picture. The p-value tells us our result isn't that surprising. The effect size tells us we actually saw a potentially meaningful difference. And that confidence interval, our range of believability, it shows our uncertainty. It shows the true average could plausibly be 50, but it could also be way up at 57.3. So the real conclusion here isn't there's no effect. It's this is interesting, but our evidence isn't strong enough. We need more data. And this brings us right to the ultimate takeaway, and it's put perfectly by the American Statistical Association. The p-value is a useful tool. It's one piece of a bigger puzzle. It is there to support the analysis, not to replace it. So I'm going to leave you with this. The next time you read a news article or see a study that says some finding was statistically significant, you are now prepared to be the smart person in the room. You can now ask the most important follow-up question of all. Okay, but how big was the effect?